What up, Calc 3? All right, here we go. Let's get this rolling. We're section 12.2, and we're dealing with vectors today. We did some of this stuff in BC, but we get into it even a little bit more now. Now, first objective, we define the component form of a vector. We kind of have it like a component in a standard form, okay? A vector, important thing that you need to recognize about a vector is a vector has two important qualities, okay? It measures both a magnitude and a direction. Use this a lot in physics, right? I know we don't have AP physics here, and we don't have AP physics here with calculus, but we have algebra-based physics. Calculus does enable us to do quite a bit more in the world of physics, and where it has a relationship is with ideas like displacement, velocity, and force, okay? But in regards to vector, a vector can go from one point to another point, okay? And it will have a magnitude and it does have a direction. Okay, if we call this A, wherever we initiate, okay, is what we call our initial point, okay? And wherever we end or terminate, okay, we call our terminal point, okay? So we have an initial point, we have a terminal point. We could use, there's a lot of different notations for vectors. Sometimes we'll just call it a U and we'll put a little boom, a little vector dude up on top, okay? Some books will just highlight it like crazy. Now you wouldn't want to do that, okay? That'd be a little nutty. So sometimes we just put a U if we just use a single letter to represent the vector, or we could go A to B. Okay, now the one thing you need to understand is if we use this notation with the initial point and the terminal point, that the direction of that vector that we use up top is significantly different, and it's important. For example, that is not equal to BA. Okay, that goes in it might have the same magnitude, but it goes in a different direction, right? That means your initial point would be B, and you would go out this way. Okay, that would be vector BA. Okay, so it's important to understand the difference between those two. Okay, we say that two vectors are equivalent or equal to each other if they have the same length and same direction. We'll get into that in a little bit. And then we do have a zero vector. That would be like a zero highlighted like crazy. Okay, and we say it has a length of zero and no direction. That'd be like the no vector, okay, or zero. Okay, next page. Let's keep rolling, guys. Vector addition, okay? Let's say we have a U and V, okay, and let's say we have an initial point of V, okay, and we terminate at U. Then U plus V is the vector from the initial point of U to the terminal point of V. All right, so what the heck does that mean? Well, let's say we have a couple of vectors, okay. Let's say we have a vector, and we'll call that guy U, okay. It's kind of where we initiate, okay. And I know it said initial point V, but now it says U plus V would be from U to V. Okay, so we're going to go ahead and initiate there. And then let's say we have another vector, boom, okay, and we'll call that guy V. Then vector addition is simply, here I'll use a different color for this, the vector from U to where V ended up. Okay, and that would be what we call vector addition. That'd be U plus V. Okay, booyah, that's it. All right, and so the question is, let's go ahead and reverse this bad boy. Okay, let's say I did V first, and did U second. So this time let's do V first. Okay, let's say we initiate with V, kind of like it said in the definition there. And then U would go what? It'd go off in that direction. So it'd be like that. Okay, so that would be U. And then V plus U. And what I'm doing here is I'm trying to see if vector addition has the property of, has the commutative property. Okay, and if you look, it does. Because U plus V is equal to V plus U. So then we would say vector addition is commutative, okay? And we do have scalar multiplication, and I think a picture does justice best for this. Okay, if you have your vector V, you could multiply it by 2. You could take half of it. That's multiplying by 2. You could take half of it. If we put a negative out in front, then it has opposite direction, okay? Same length, though. Okay, but a different direction, same magnitude. And then this last one would be like a negative, which would mean a different direction. And then if I multiply it by 1.5, it also has a different magnitude. Okay, so that's what scalars would do when we multiplied it by certain vectors. Okay, boom, let's keep rolling here. All right, now how would we look at the difference between two vectors u and v? Well, going back to when subtraction was first created, the people way back in the day would relate a difference with addition. Okay, so they would kind of do that. Okay, they define what a negative scalar would do, or a negative number would do, and then they looked at a relationship. So let's go ahead and look at this. We're going to create a u. Okay, let's say that's u. Okay, so that's u. Okay, and let's say v is, let's say it goes off like in this direction here and has that magnitude. Okay, and that's v. And let's say we want to do u into, I want to add, so that means at the end of that, I'm going to add my v, which would be go down like this. Boom. Ooh, shame on me, shame on me. I'm going to do the opposite of it, right, you guys? I'm going to do negative. I'm going to add to it negative. So that means it would go off in the other direction. So gosh darn it, hopefully I don't run out of room, but it'd have to be the same direction and magnitude, and that'd be v. Okay, and then u plus v, u plus negative v, or u minus v, would be from the initial to the terminant. That'd be u plus negative v, which we actually do find is equivalent to u minus vector v. Okay, and that would be what we call the difference between the two. So there you go. Easy peasy, right? Not too bad. Okay, now your job at home is to do this and then hit pause. Okay, if a and b are vectors shown in figure 9, then what would a minus 2 be? Okay, so your job is to hit pause right now. After you hit pause, I'm going to go ahead and unveil, okay, ichi ni, well, hopefully you hit pause, ichi ni sanban, okay? Hopefully you got that as your answer. And that'd just be a plus negative 2b, or in this case, a minus 2b. But then we do the same thing if we wanted to represent it graphically. Okay? All right, let's keep rolling. All right, coordinate systems. Let's say we have a vector in, this would be in 2 space. Okay, this would be in 3 space. Okay, and let's say we have a initial point and we have a terminal point. Okay, P1 being the initial point, P2 being the terminal point. Okay, and we're in 2 dimensions here. Okay, so we have 1, 3. 1, 2, 3. That would be P1, and that'd be 4, negative 2. That'd be P2. Thus, the vector has this direction and that magnitude. Okay, and I don't know if it really should say bracket. These fancy dudes right here are called chevrons, right? And we should remember that from our BC days. But if I wanted to write this in vector notation, bracket notation, chevronish notation, it's actually just chevron notation, you do the terminal for minus the initial, ichiban, okay? The terminal, negative 2, minus the initial, which would be 3. So another way to represent this vector P1, P2 would be 3, negative 5. And what happens if I graphed 3, negative 5? And I'm going to make it a different color here. I'm going to make it green. 3, 1, 2, 3, 4, 5. Believe it or not, we usually represent these vectors as extending from the origin. And you could have, an infinite amount of these bad boys. And as long as they have the same direction, same magnitude, then we say they're equivalent to one another. A good way of showing this is this cool picture that I have here, okay? Which is that guy. Those guys are all representations of the vector 3, 2. Okay? Chevrons like that means we say that it is in component form. Okay? Not too bad, right, you guys? And we can extend this, obviously, to 3 dimensions. Do I have a problem? Ooh, how about it I do? So your job, again, take some good notes on this. Okay, I think this is an additional problem I had in there. And then what I want you to do is see if you can give me the vector that's represented by those 2 points, right? If you notice, there's not chevrons. So those are points in our 3 space. And then what I want you to do is give me the vector component form of it. Okay, hit pause. Go ahead and give it a shot. And unveil it! Okay, there's your answer. If you got negative 4, 4, negative 3, then you did it beautifully. And remember, that's just the terminal minus the initial for each one of those components. Okay, thus called component form. All right, We have some arithmetic operations for vectors. They're all right there. I think they're pretty common sense. You either add them by adding your each component form with each other, or you subtract them, you subtract the components of each other, or if you have a scalar, you can distribute that scalar within. Okay, so your job right now, once again, is to try these guys, hit pause, and let's see if we get the same answer. Okay, all right, so hopefully you tried it and you hit pause, but I'm simply going to add those two vectors together. I'm not going to show our work, right? We're in Calc 3 right now. If you do everything correctly, you should get 1, 5, and I'm adding these, so negative tribon, okay? And then b minus 2a. If you do that correctly, you should get b minus, and you're going to double that. So that would be a 3 and a negative 4. 3, and it's a minus, right? And we're going to multiply by 2, so that would give me a 7. That would be the b, which is 5 minus 0, which would be 5. And then it would be negative 4 minus 2, which would be negative 6. Boom. All right. Make sure you come in for extra help if you guys need it. Do I have an extra little practice problem here at the bottom? I do not, so let's just keep going. I don't want these videos to be too long. You have all of these properties you need to know. Okay, when we have something that I feel like is really important, I really want to make sure I have your focus, we'll do it in class. So your job next class is say, Mr. T, let's go ahead and do this proof together. Okay, which means you might have to do a proof in the future, so make sure you remind me of that, okay? But we don't want this video to run too long, okay? Unit vectors, okay? We did do unit vectors in BC also, okay? But we want to be able to define unit vectors for our I, J, and K vectors and recognize their importance of each one of those. If we're in 2 space, our unit vectors are always of length 1. So our I component unit vector would be 1, 0. J would be 0, 1. If we go to 3 space, we add the third dimension, which is the K component, which would be 0, 0, 1. And those are all called unit vectors. Why? Because they all have a length of 1. We'll get into length and magnitude a little bit later on. We did some of that in BC. Okay? I, J, and K are called unit or standard base vectors. They all have a length of 1, and they all point in the positive direction. Okay, so if you have a Z, a X, and a Y, there is your unit vector I. Okay, here's your unit vector J, and here's your unit vector K. And remember, if they're vectors, they'd all point out in those directions, and they all would have a length of 1. Okay? All right. This is almost an extension of what we just got doing in the last little piece, but you can add these 2 vectors together here. This is what we call the standard form when we put our I's, J's, and K's. You could write this instead. You could write your vector A, you guys, as 1, 2, negative 3. Some people like the component form better. It's kind of to each their own. The rule that I like to use is that'd be 4, there's no J, so that'd be 0, and that'd be 7. The rule I usually like to use, and so do a lot of textbooks, is if the problem is given to you in standard form with the unit vectors I, J, and K, then that means it wants you to give your answers in terms of I's, J's, and K's. Okay, you can always use what you like to work with best, but if you do this problem right here correctly, you should get an answer of 14I, okay? And you either have to really bold that I or we put the little vector above it, okay? And that would be plus 4J plus 15K. Okay, and once again, that's just in our standard form. If you wanted to, you could put it in component form, but like I said earlier, if they give you something in component form, then give component form as your answer and vice versa. Standard, go ahead and give us some standard. Okay? All right, here we go. Now we get to magnitude. Now magnitude can be represented 2 ways in our textbooks or Calc 3 textbooks. A single line, not absolute value, but that means magnitude. That's how you found the magnitude in 2 space. Okay? That also can use magnitude if we use those 2 dudes. Okay, so just make sure you're familiar with both of those. If we extend this to 3 space, okay, then it's simply v1 squared plus v2 squared plus v3 squared. That's it if you have your 3 different vectors, okay? In this particular example, look, we're in 3 space. We have u as I minus 3j plus 3k, standard form with our unit vectors, and v is I plus j, so that means k would be 0. All right, so simply, we're going to take the magnitude of u magnitude of u would simply be 1 squared plus negative 3 squared plus 2 squared. Okay, and we're going to add that to the magnitude of v, which would simply be 1 squared plus 1 squared plus 0 squared, which if we do ijk, so if we do all of that correctly, we get the square root of what would that be? That'd be 14 plus the square root of 2. That's it. That's all you do for that. Not bad at all, right? This one here, let's go ahead and see if magnitude can be distributed, right? If it could, we would get the same answer, but we're going to add those two vectors together first, and if I do that, I get 2i minus 2j plus 2k, right? And so in order to find the magnitude of that, it's simply 2 squared plus negative 2 squared plus 2 squared, okay, which would be equal to the square root of 12, which would be 2 radical 3. They are not equal to each other, okay? The next guy has a big time importance, okay? Remember, the magnitude of v was 1 over the square root of 2, and I'm going to multiply that by the vector v, which would be I plus j. Okay, ooh, if I put it in component form, darn it. I put it in component form there, and I think it's a little, and it just says v there, so you can do it any way you'd like, but that'd be 1 comma 1 comma 0. Okay, and if I distribute that in, I get 1 over radical 2, comma 1 over radical 2, comma 0. And if it's 0, you also can represent it this way. Okay, and I know that might look like it's in 2 dimensions, but it actually doesn't matter. Now, I can use i's and j's too. Now, the one thing that's interesting to note right here is A and B, I got answers that were scalars, and C, I got a vector. Why did I get a vector? Because I took the 1 over the magnitude and I multiplied it by a vector, thus creating a vector. And it's important sometimes to realize, am I supposed to get a vector as my answer or a scalar as my answer? Okay, just like this last piece here, right? Now you're going to take the magnitude of what I just got. And if I take the magnitude of what I just got, that means I should get a scalar as an answer. And that would simply be the square root of 1 over the square root of 2 squared plus 1 over the square root of 2 squared, which would be the square root of 1/2 plus 1/2, which is the square root of 1, which is ichiban, which, if you take, and we already went over this earlier, if you can take the magnitude of your vector and that answer or the length of it is 1, then we have what we call a unit vector. And believe it or not, you will always create a unit vector if you take your vector and you divide it by its magnitude. Okay, that will always create and give us a unit vector. Okay, very important to note. Can you do it on your own? Find the unit vector in the direction of A. So I want that guy's unit vector, okay? Your job is to hit pause and hit it right now. And whenever you do this and you find the unit vector, it's called normalizing your vector, okay? So I want you to normalize this vector here. What would you do? Hit pause and see if you can do it. Unpause it. Here we go. Well, I just got done saying that you can always find a unit vector if you do 1 over the magnitude of it, and then you multiply it by your vector. Boom. That's always going to give us a unit vector. Okay, well, what would that be? Well, the magnitude of my vector would be the square root of 2 squared plus 1 squared plus 2 squared, okay, which would be the square root of 9, which would be 3. Okay, so that'd be 1 over 3. And I'm going to keep it in component form. I just think it's easier to work with it in component form personally. To each their own. I know they give it to us like that, so then I could write it with a final answer of that, right? 100, right? I just think it's easier like that way, but then, hey, at the end, you could do a little I, a J, a K. And guess what? Guess what I am going to get as an answer if I take the magnitude of it. So if I go a little spling, right? If I go a little spling, if I do that, I get ichiban. Go ahead and check me. Go ahead and check it. And so I just normalized that vector. I just normalized it, okay? Because by getting the unit vector. Okay? Ooh, do I have anything else? I don't. I think I have one more that I might want you to try. Okay. I think we end the lesson. Yes, we end the lesson here. And then the last 2 examples we do in class, because they're kind of some doozies. Okay, and I want to make sure, once again, when we do these doozies or like the superstar problems or the really important dudes, I need to know that you are straight up locked. Okay, I need you to be locked. Okay, all right, here we go. Define the polar form of a vector. This is considered the polar form of a vector. And you know what's really interesting about this, dude, is if I divide the magnitude of that, you should say, yo, Mr. T, that would be normalizing it. And I would say, you know what, you're right. That would be normalizing it. And do you know what's really interesting? Is if you take the magnitude of this, what should I get as my answer? Ichiban! Right? And if you normalize this, right, what would I get? I would get cosine squared theta plus sine squared theta, which is Ichiban! Isn't that awesome how that works out? I think it is crazy awesome how that works out. I really, really do. Okay. And so this is going to become important with the application problems we're going to do next class. Okay, example 7 says to find the angle that V, our vector V, right? It's either really highlighted or we put that on top of it. Okay, our vector V is a negative radical 3 comma 1, and I want to know what angle it is between that dude and the positive x-axis. So if I kind of wanted to draw it out, negative radical 3, that'd be a little bit more than 1, like 1.7, up 1. So you have your vector right there. And I am trying to find that angle right there. Boom. I don't know about you, but that looks like it's in the second quadrant. Okay, now, you don't have to draw these out. You very easily could use the polar form of a vector in order to find it. Okay, which would be your vector V, which is negative radical 3 comma 1. Okay, and that is equal to the magnitude of that vector, which would be the square root of, gosh, what would that be? It'd be that, which would be 3 plus 1, so I get the square root of 4, which would be 2, times cosine theta, sine theta. Boom. And you guys actually could maybe get this on your own. I'd be pretty impressed if you could. I'm trying to find the angle. Well, if I'm trying to find the angle, aren't I trying to get theta by itself? Yes, you are, Mr. T, so let's do it. Square root of 4 is 2. I'm going to bring it over to the other side. And then I can multiply a scalar within a vector, so I get that. Oh, snap. So now all I have to do is match up my components. Okay, your I component says that cosine theta has to be equal to negative radical 3. And your J component says that sine of theta equals 1/2. Well, I don't even need a calculator to do that because I remember from my pre-calc A, B, B, C days that only happens at a 30-degree reference angle. But that 30-degree reference angle has to be in the second quadrant, so that means that's 30 degrees or pi over 6, or in this case is 5 pi over 6. So theta is equal to 5 pi over 6. Come on, Mr. T, you got to challenge me better than that. Yes, sir. Yes, sir. All right, some people said they missed Homie Holmes. So there's Homie Holmes, and last year we got the gingerbread man. All right, that's your video. That's as goofy as I can get in Calc 3. These two application problems we will do in class. They're very important. They relate physics with calc, which is really, really cool, but that's your video today. Watch your videos, do your homework, get ready for quizzes and tests. Aloha!